Hi, in this video we will be talking about particles in detail. We all know that matter is anything that has mass and occupies space. Also, that all matter is made up of atoms. Even if you are not a chemistry student, you must already know the subatomic particles that make up the atom: the protons, neutrons, and the electrons. The protons and neutrons are in the central positively charged nucleus of the atom, and they experience the strong nuclear force. Particles can be divided into certain groups according to their properties. Hadrons are particles that experience the strong nuclear force and are composed of smaller particles called quarks. Quarks, if you are wondering, are fundamental particles and the building blocks of hadrons. Three types of quarks, up, down, and strange, have different properties which can give different hadron compositions when combined. Strange quarks have a property called strangeness. Strangeness is a quantum number that is created via strong interaction and decays via weak interaction. It can only be conserved in strong interactions. Hadrons are subdivided into two groups. 1. Baryons are hadrons that are made up of three quarks. Examples of baryons include the protons and neutrons. Protons are the only stable baryons. Neutrons are unstable. They decay to become other particles plus proton. Baryon number is the number of baryons in an interaction. Protons and neutrons have a baryon number B equals +1 or +1. It is a quantum number that is conserved in any interaction. During an interaction, baryon number on either side of that interaction has to be the same or equal. Antiquarks make up antiparticles, such as antiprotons or antineutrons, and etc. Antiparticles are annihilated when they meet the corresponding particle. That's why antibaryons are not found in ordinary matter. 2. Mesons are hadrons that are made up of two quarks. All mesons are unstable and have a baryon number 0. Pions are the lightest mesons. Kaons are heavier and more unstable. They have a very short lifetime and decay into pions. Leptons are fundamental particles that don't feel the strong nuclear force. Types of leptons are the electrons, which are stable, muons, which are unstable and decay to form electrons, and neutrinos, which have negligible mass, no charge, and only interact through the weak interaction. Neutron decay is caused by weak interaction. It involves a neutron changing into a proton. This happens when there are more neutrons than protons in a nucleus, or when a neutron is by itself outside of a nucleus. When a neutron decays, it forms a proton, an electron, and an antineutrino.
Now, all particles obey a certain set of conservation laws, and these laws can be very useful in determining which particles you may get out of a reaction. And the common exam question that you can get is kind of deducing what kind of particles are coming in or what particles are going out. And or maybe you're given a reaction and you're asked to see whether this reaction obeys all of the conservation laws. So they're pretty useful. Now, remember, anything that is said to be conserved, it basically means, is it the same before and after a reaction? So it is conserved if it is the same before the reaction as it is after the reaction. So let's start by looking at the conservation of charge. And charge is a quantity that is conserved in all particle reactions. And so what's it saying? It says that the total charge before the reaction is the same as the total charge after reaction. So let's take the example of beta minus decay. So let's draw out let's just write down the equation for beta minus decay. So we have the neutron turning into a proton plus an electron, electron neutrino, just for some reason I wrote that one first, plus the electron there. So anti-electron neutrino plus the electron. So let's have a look and see if charge is conserved. Well, what's the charge on this side of the reaction? On this side, we've only got the neutron, and of course the neutron is neutral, so on this side we simply have 0. And what is the total charge on this side of the reaction? Well, here we've got the proton, which is a charge of +1, the anti-electron neutrino, which is of course, well, it's a neutrino, so it's got no charge at all, and the electron, which of course is negatively charged. So we have +1, +0, -1. What does that add to? 0. So we can see that the charge before the reaction and after the reaction is the same. And so therefore charge is conserved. The next thing that is conserved is baryon number. And again, baryon number is, of course, simply the number of baryons present. So a proton would have a baryon number of +1, a neutron would have a baryon number of +1, a pion would have a baryon number of 0, an electron would have a baryon number of 0. You get the idea. It's basically just the number of baryons. And maybe I should say that the antiproton has a baryon number of -1. So let's use the example of beta minus decay again. So let's just write it out. So a neutron turns into a proton plus an electron. I'll write it in the normal way around this time. Plus the electron anti-neutrino. So let's have a look at baryon number before and after. Well, what have we got on the left-hand side? We've got the neutron, again, just a neutron. And, well, the neutron is a type of baryon. And so it has a baryon number of +1. So what about the right-hand side? Well, on the right-hand side, we've got the proton, which is, of course, a baryon. But we've also got the electron, which isn't a baryon, so it has a baryon number of 0. Plus the electron anti-neutrino, which, again, is a lepton. It's not a baryon, so it's going to have a baryon number of 0. So what are these total? Well, before we got 1 on this hand side and 1 on this hand side. So again, baryon number is conserved. Now next we have the quantity of lepton number. And unfortunately this one is a bit more complicated. You see, with baryon number, we just simply compared the number of baryons on this side with the number of baryons on this side. However, instead of doing the same thing with leptons, we actually conserve lepton numbers for each branch of leptons. And so, remember I said before the types of leptons were the electron, the muon, and the tau. And each of these electrons had their own neutrinos. So you had the electron neutrino, the mu neutrino, and the tau neutrino. And all of these, of course, have their own antiparticles. So these guys all have, they're all leptons, but they all have different respective lepton numbers. So these two guys right here, they have an electron lepton number of +1, whereas all these guys right here, they got nothing to do with electrons, so they all have an electron lepton number of 0. However, that's only electron lepton number. If we look at mu lepton number, then these guys, they're nothing to do with mu's, and neither are these guys right here. These guys are going to have a mu lepton number of +1. But the mu lepton number is a different quantity to the electron lepton number. And so it's a different thing that has to be conserved. So let's take the reaction in which a positive muon decays into an positron plus an anti-mu neutrino and an electron neutrino. So let's count the respective lepton number before and after. And let's start with electron lepton number. So what's the electron lepton number of this side of the reaction? Well, this is a positively charged muon, an anti-muon, got nothing to do with electrons, so it's going to be 0. What about this hand side? Well, we've got the positron. Now the positron is an antiparticle, remember, and so it's going to have a electron-lepton number of -1. So you see all these guys, these are all normal particles, and therefore their corresponding antiparticles are going to just have the sign reversed. So the positron has a electron-lepton number of -1, and this anti-mu neutrino, that's nothing to do with electrons, so it's 0. And we've got the electron neutrino. Now that's a normal particle, it's not an antiparticle, so that's going to have a electron-lepton number of 1. So do these two sides equal? Well, yes they do. 0 equals -1 plus 0 plus 1. These two just add to give 0, and so electron-lepton number before and after this reaction is 0. And the final thing that is conserved is strangeness. So just to recap, we found that kaons are the particles which have strangeness. None of these other ones have strangeness, it's just the kaons because they're the only ones that contain strange quarks. And remember I said that the normal strange quark actually has a strangeness of -1, and the anti-strange quark has a strangeness of +1. Now, strangeness is only conserved in reactions which involve the strong force. Now, it might be worth making a note of that. It's only conserved in strong force interactions. If it's a weak interaction, then the strangeness doesn't necessarily have to be conserved. It could be, but it's not conserved in all interactions. So it's only interactions involving the strong force in which strangeness is conserved. So let's do one final example showing the conservation of strangeness. So we have a pi minus meson plus a proton goes into a kaon plus this new particle which is called the lambda. And you may be asking, what's this lambda particle? Well, you don't have to know it, don't worry. But its quark composition is up-down strange. So it's not one that you have to know, but you may be given a question in which you are given an unknown particle, but you have to use what you know about conservation laws and the quarks you do know about to maybe deduce something about particles that you don't know about. So you don't actually have to know that this particle exists. I'm just using it for this example. So let's see if strangeness is conserved in this reaction. Well, we have, what is the strangeness on this side? It is, well, the pion's not strange. It's a perfectly normal particle. And the proton isn't strange either, so there's no strangeness on this side. What about this side? Well, the normal kaon, the K0, not the K bar 0, but we're just dealing with a normal kaon right here, it had the quark composition of up anti-strange. But of course, anti-strange has a strangeness of +1. And the normal strange quark has a strangeness of -1. So this guy right here has a strangeness of -1. The K0 has a strangeness of +1. Add these two together, we just get 0. So we can see that strangeness is conserved in this reaction.